Hello, everybody. So for this iteration of the network theory reading groups, I'm going to present a paper entitled Stability Conditions for Discrete-Time Decentralized Medium Access Algorithm. So it's a paper that was written by Shneer and Stolyar and published in 2018. So as an introduction, so medium access control, it's something that is used in communication theory. So this kind of algorithm are in charge of deciding who has access to control. So it can be in wireless network, or it can be in other type of communication networks. No, merci. So medium access protocol is a protocol that prevents neighbors from transmitting simultaneously, because when you have two neighbors that are transmitting at the same time, you may have collision and loss of packet. So using this type of protocol prevents this phenomena that we don't really want to have ideally in a network communication. And so the goal that we want in most of this kind of system is something which is called maximal stability. So all nodes in the network can transmit the arriving packets in a finite time for all different arriving processes, so not for just a subclass of processes, but we want this result to be as general as possible. And so the goal that we want to achieve is maximal stability. So centralized algorithms have been developed already. So for example, we have a max weight algorithm, or a class of algorithm is called alpha fair algorithm. So these algorithms are known to be maximally stable for all different arriving processes. But the problem for this centralized algorithm is that, as the name says, you need a centralized controller to make all the decisions in the network, and it can be very costly in terms of computing time. So it's not an ideal solution, even though it works quite well in some cases. And so this led to developing decentralized algorithms. So the one that we're going to study here is something called CSMA, Carrier Sense Multiple Access. It has already so it's normalized in the norm I3 802.11. So it's something that is already implemented in practice. So in this setup, so nodes have a random back of time. So if I'm a node in the network, I'm going to start transmitting, and if I hear one of my neighbors that is already transmitting, then I will draw a random variable that consists in the back of time. So I'm stopping transmitting and I wait a random amount of time, and then I restart my transmission. And if I don't see any other one transmitting, I can go on with my transmission. And when I start transmitting, I already hear someone transmitting, then I'm going just to draw another back of time randomly up until I can transmit the packet that I have. So this is the setup of CSMA. So the intuition behind the decentralized algorithm is that it can be very computationally effective, because you don't need to have one central controller that makes all the decisions. And it can also be interesting because you only need very local properties of your network, and you don't need to know the general topology of the network. Also, another thing that is interesting is that most of the results are now for something which is called saturated networks, where all the nodes are always transmitting, so they always have packets to transmit. And the thing is that if you cannot generalize the already known results to unsaturated networks, where you allow nodes that don't have any packet to transmit to exit the network. So these are two very different things to study, and we cannot generalize the results from one to another. The second thing that is a big problem is that the processes are not something which is called monotonous. So monotonicity is something which is quite interesting in Turing theory to have. If we have two arriving processes that are different, and one is something that's called dominates, meaning that the condition at all times for all nodes in the network in one arriving process is greater than the second one. If the stochastic processes are monotonous, you can exhibit some coupling of the two processes such that this kind of monotonicity is conserved at all times in the network. And so this property is very useful because you can always try to think of nice dominating processes for which the stability conditions are very easy to achieve. But the problem is that in most of these medium access algorithms, you do not have this monotonicity, and the stability can be hard to achieve. And so these two problems have led to the development of queue-based algorithms. So these queue-based algorithms, so they can give you a different queuing disciplines that are very depending on the size of the queue of each node in the network. And so it was proven that this algorithm can provide with maximal stability, but in practice, they are quite difficult to implement, and they also can lead to very high delays in the network. So even though you have maximal stability, the expected amount of time that you wait before being able to transmit is quite high, and it can be detrimental to network performance. And so in this case, we are going to remove most of this assumption, and we want to have something which is called standard CSMA. And so it consists in three assumptions. So first, each node does not know its neighbors. We only know if we have a transmission happening in our neighborhood, but we are not making an active procedure to discover who are our neighbors and some other properties of the neighbor nodes in the network. We also assume that the access procedure is the same for all nodes. So which in the following of the paper, it will lead to some nice properties based on the topology. And we also assume that a node does not access the network if its queue length is empty. So if we do not have anything to transmit, then the node is put in standby and it does not try to transmit anything. And so these three hypotheses actually can model a very large array of networks. And the fact that and mathematically speaking can be interesting because we do not have any kind of preferential node in the network because the access procedure is the same for all nodes. So now we can see how we can model this in terms of mathematics. So we are going only to consider here two very simple topologies. So we assume that we have n transmitter nodes that are either in a circle or a line. So here just two small drawings to some people have forgotten what is a circle and what is a line. But what's going to be very interesting, actually these two topologies are very different because for the circle topology, every node is the same wherever you are put in a circle. But when you look at the line topology, actually you have two very important nodes that are extremely different from the rest of the other ones, is the two end nodes of the line. And actually we'll see that it can lead to some problems when talking about stability. We also assume that the nodes have infinite buffer space, so we can have as many packets waiting for transmission as possible. We assume that time is slotted. Sorry, transmission time is equal to 1. Then some definitions. So we have the queue size process. We have an arrival process xi, and so we assume that it's IID with and we denote as lambda the waiting time. The average number of arrivals in a time slot. So one very good example of such an arrival process is just the classical Poisson process, but it can be linked to any kind of arriving process with finite first order measure. And now to model the CSMA property, stating that you do not transmit if one of your neighbors is transmitting. What we do is that we are going to select something which is called a time priority. So we allocate a random time priority and to decide which nodes are transmitting. So we take the node with priority 1 and we set it to transmitting, and then we deactivate its two neighbors. And then we post it by induction in the network. So we take the next highest priority. We decide to, if it's not already deactivated, it transmits and it blocks transmission for its two neighbors. And we repeat it until no node can transmit. So just as an example, we can see here we have 8 nodes. So just I picked a random priority allocation. So here the node with the highest priority is node number 2. So we set it to transmitting. We block the transmission from node 1 and 3. We repeat. So node 1 has a priority 2, but it cannot transmit. So we move to node with priority 3, which is node 6. It transmits. It blocks the transmission for its two neighbors. And then,
excuse me, it's Konstantin Avrachenko. I assume we can ask questions, right, during the presentation, or we have to wait until the end.
You can ask question if you have.
So you mentioned that the protocol will be fully distributed. So is it some auxiliary protocol with priorities? Because at first sight it doesn't seem like fully distributed, right? Everyone needs to know all priorities.
Actually, we need to define this priority because we are looking at the network from an outside perspective. But from the inside perspective of the network, actually, these priorities actually are purely artificial. What is done here with these priorities actually is exactly what I described as the CSMA, meaning that the medium access, sorry, you cannot transmit if one of your neighbors is already transmitting. So here what happens is that at the beginning of each time slot, from the outside perspective, we assign these priorities, but actually it's just the way to decide which nodes are transmitting. So actually this does not take any amount of time in the network, and it's purely artificial to describe the dynamics of the network. From the node perspective, actually, it's just the property as you do not transmit if one of your neighbors is already transmitting. And so what happens is that at the beginning of each time slot, from the outside perspective, we draw these priorities, and then we allocate which nodes are transmitting. But from the inside perspective of a node, actually, it does not matter. The node is only transmitting if none of its neighbors is transmitting. So it's purely artificial and it's purely distributed in practice.
So, sorry, I have a question.
Yes.
Is for 8 and 6, is this a typo or I missed something?
So here actually, yeah, it may be a bit confusing. So in the figure, I just numbered the nodes as so I decided that the node number 1 is the one on the top, and then after I went clockwise. And then the priority, so here the priority, for example, priority for node 1 is 2, priority for node 2 is 1, and for example, priority for node 8 is 4. So this is just this priority allocation. And then after I just use the procedure that I mentioned earlier. So here we looked at the priority for each node, and we take the node with priority 1, which is here the node number 2. It transmits. Yes.
Thank you.
Yes. So yeah, sorry, it may be a bit confusing. I should have made it a bit clearer.
There's 2 4s and a 7
Oh yeah, sorry. Yeah, sorry. So the 7 should be here. Yeah, I see what you mean. Sorry for this.
Yeah.
Yes.
They don't transmit to another node, right? They transmit somewhere, but
so technically it's a single hop system. So yeah, so you transmit in all directions,
okay,
but not to another node in particular. So you transmit to all of your neighbors at the same time.
Okay.
So here is like assuming that you not have an division at the beginning, every time slot, everybody is multiplying the funnel in a right way.
Yes.
Okay.
Yes, and so like I said, it's a single hop system. So you are transmitting to all of your neighbors at the same time, and when the packet is transmitted, it leaves the system. So there are no rerouting. It's not a multi-hop network, so just a basic single hop system. And if we denote as DI the number of packet transmission at a given node and for a given time slot, then we have a very simple temporal evolution for the queue at node I. So it's a Markov jump process. You just add the number of arriving packets and you remove the number of transmitted packets. And so DI can only be equal to 0 or 1 because you can only transmit at most 1 packet per unit of time. And so actually this problem is it can be reduced to another known queuing theory problem, which is the parking problem, or the jamming, the parking constant on line. And so here, if we decide that the transmitting node at the node where a car decides to park, and we assume that our cars have a length equal to 2. And so if a car is parked, it will block the 2 extremities of its parking slot. And then we can reduce ourselves to the parking problem, which has already been studied very longly in queuing theory processes. And we have some results about something which is called the parking constant, or it's also known as the jamming density, which is the maximum number of cars that can be parked in a line with a slotted space. Oh, sorry, the references have not passed. I'm going to give them at the end of the talk. But if so we can see that the number of transmitting nodes actually can be reduced to the number of departures in a line of k non-empty nodes, and it can be also reduced to the number of cars that are parked in the parking lot of k slots. And so we have, since we have some known results about this thing, we are going to use them in the first time in this problem. So, for example, a very interesting thing to see is that if we decide, so if we have a line that are consisting of k nodes, if we add any given number of nodes at the end of this line, then it's going to decrease the number of departures. And so how we can, so a way to interpret this result is that if we add transmission to our network, if we add noise, then we're going to decrease the number of departures. So to see why, if we take here the red line, there are going to be a given amount of nodes that are transmitting in this line. And if we add nodes at the end of the line, maybe for some given priority allocation, this node is going to transmit. And because this node is going to transmit, it's going to block one of the nodes in the red line, and it will decrease the expected number of departures among these first k nodes. So I'm not going to go through much of the details here, but it's just a proof by induction. And we simply make the average, and we just compute the average number of departures in the first k nodes in the whole line, and we compare the two quantities, and we can see that having transmission in these end nodes actually blocks the number of departures that we have at the beginning of the line. And as a consequence, we have some kind of convex property. So if we take a node of k plus m and we merge these two lines, then the expected number of departures is going to be lower because we have some kind of interference at the point in which these two lines merges.
So Pierre, can I ask a question?
Yes.
So you're saying it's the expected number of departures, but expected with respect to what probability distribution? Like, is it the distribution of priorities or like stationarity or?
So this is when you look at when you talk about the expected number of departures, that if we take a random, so I will go back to this priority allocation, but if we take this priority allocation, we are looking at the average among all the possible priority allocation. And this is going to determine what nodes are being able to transmit, and ultimately what is the expected number of transmission in the network. And
every priority is equally likely.
Yes, we assume that all the priority allocations are distributed randomly and uniformly.
Thank you.
So now we have a first result when it comes to stability. So here the L, so L is going to denote the parking constant on a line, and then C is going to denote the constant parking on a circle. So we have a known result that can link the expected number of departures in a circle and the number of departures in a line. So if we have a circle with n nodes, actually the number of departures in a circle with n nodes is the number of departures in a line with n minus 3 nodes plus 1. So this is so I didn't note it, but it's just to see it. If you look at a circle, you take one node, you decide to remove it, you have a line with n minus 3 nodes, and then the number of cars that you can park or the number of nodes that can transmit, you simply have to add 1 because there's only one possible node that can transmit on the nodes that you removed from the line. So now, so this is just a very basic result. So we introduced something which is called reshuffling. So in this reshuffling, we have 3 versions that are very similar. So the first version is just the basic reshuffling. We take all the queue length. We decide to shuffle them among all the possible nodes in the network. And this is the first reshuffling. The reshuffling is taken uniformly at random. Yes.
So you do that at every time slot?
At the beginning of every time slot. Then the second version is a bit more refined. So the empty queues stay where they are, and we reshuffle only the non-empty queues. So this is the second version of the reshuffling. And the last thing is that all the non-empty queues are reshuffled, and actually within each non-empty segment. So if we have empty queues, we can reduce the analysis to non-empty queues. And then there are going to be a certain number of non-empty queues that are contiguous in the network. And we only make the reshuffling inside each non-empty segment. But actually, this is so which version of the reshuffling we take is not very important, because we have the same stability condition for the 3 reshufflings. So for the circle topology, it has to, the arriving number has to be lower than the jamming density in a circle. And for the line topology, it has to be lower than the jamming density for a line. And it also has to be lesser than one half. So this stability condition actually comes from the very basic fact that if you want to have stability in a Markov chain, the average number of arrival has to be lower than the average number of departures. And it works because since you have reshuffling, there is no particular point that you can look at in the network, and so it works for if the average number of departures is going to be equal to this jamming density. So this is so it only uses this basic property of Markov jump processes. And so now we are going to remove reshuffling and stop actually. Yes, it is a sufficient condition. So it's not. It is a sufficient condition. We do not know if the maximum arrival, the maximum arrival rate is equal to this jamming constant. So the reciprocal is not true. Is not particularly true. So we do not know actually if the state. So we know that the system is always unstable if lambda is greater than these 2 constants, but we do not know if the maximum stability. If the stability region is equal to this line. So now we're going to remove this reshuffling because so it's a bit let's say it's a bit of a cheating, because with reshuffling actually we are removing any kind of edge cases that we can get due to the topology of the network. For example, for the line, we are removing the fact that the 2 end nodes actually transmit less than the rest of the line. So now we're going to prove. So start with a loose stability condition. So the way to do this is just through the very classical way. So using the Stolyar theorem. So if we take a pi-reducible discrete-time Markov chain, which is our case here, to prove the stability. So this is a necessary and sufficient condition to have a positive Harris recurrent. I forgot the conclusion of the theorem. So if we have the drift, so the drift is just if we take the expected value of one jump in the state space, given a certain initial condition, then we want this this drift to be bounded from above inside a finite set and to be negative outside the set finite set. And so the way this is going to act, that if our initial condition is outside our finite set, then it's going to drift towards the set C in a way, in such a way that this set C actually is going to work as some kind of attractor. And when we are reaching this finite set C, we know that we are going to stay inside it, because every time we are going to make an excursion outside the set C, it's going to drift back towards it. And so the end of the theorem that I forgot to mention here is that if we have this condition, then the Markov chain is positive Harris recurrent. So positive Harris recurrence is just that the expected return time to in any finite state is going to be almost surely finite. So here, if we have a finite state space that is just the real numbers, it is needed to prove that there exists a condition constant k that if the initial condition psi has a norm that is higher than k, then the drift is going to be lesser than minus epsilon, with an epsilon strictly positive. And so the idea here is to find a suitable Lyapunov function L for our queuing network, and we can to deduce a condition on lambda for the system to be stable. And so this is going to be, so ideally this is the recipe. The problem is that the function that we have to find is a Lyapunov function. So some people say it's black magic, the way to find Lyapunov function. It mostly works on intuition. If at some point you have the right intuition for the Lyapunov function that is going to give you the right condition for lambda, it's very easy to prove, but you have a lot of work to get the said intuition. So fortunately here, the Lyapunov function is not going to be that hard to get. So we simply take the sum of the xi plus 1 squared. So this is a quite easy Lyapunov function when it comes to the whole spectrum of possible functions. And the theorem that we're going to prove is that if lambda is lesser than 3/8, and if the variance, sorry, of xi is finite, then the system is stable for both topologies. So like I said, here a very easy arrival process that matches this condition is the Poisson process, but once again, it's not the only one. So yeah. So I'm just going to show the outline of this proof because it's rather straightforward. We'll just make the computation of the drift. So if we take an initial condition, we are just going to write down what is the drift. So it's just the Lyapunov function at t is equal to 1 minus the Lyapunov function at t is equal to 0. We are making some just simple upper bounds using the triangular inequality and also squared identity. So here it's easy that on the first two terms, here we just make, so we just develop and then we make some reindexation of the sum, and we can bound from above this term using, so here this is why we need the second order of xi to be finite, because it appears naturally in the calculation. And for the rest, we use the fact that di is always lesser than 2. And so it allows us to bound everything from above using n. So the 4 comes from the 1 plus 1 squared, and lambda squared comes from the expected value of xi. So everything is rather straightforward. For the second term, we just have to make some kind of calculation. So we have naturally a 4 lambda that appears when we make some reindexation of the sum. And then here we have a sum of 3 expectations that are the expected number of departure for node i-1, i, and i+1. And so here we have to make a simple case study that is based on the whether or not nodes i-1, or i+1 are transmitting. So here, if the Q length at i-1 and i+1 is 0, none of the nodes are accessing the network. And so it means that it is node I that is transmitting. And so in the sum, we have 2 times the expected number of transmission at a time slot from node I, so which is equal to 1. So the sum is equal to 2. Now, if the Q length at node i-1 is not empty, then we may have either transmission happening at node i-1 or I, and so we have to take this into account. So node i+1 is not going to transmit, so this expected number of transmission is going to be equal to 0. And then here we're just splitting it. So we say that the expected number of transmission from node I and i-1, so the sum of the two is equal to 1 because we have either of these nodes that is transmitting. And then it reduces to 1 plus the expected number of departures from node I, and we can prove that this probability is greater than 1/2. So the sum of the two is greater than 3/2. And so it works as a symmetric for node i+1. So these two cases happen with an expected value that is greater than 3/2. And the last thing that we have to take into account is that if the two nodes may be active, and then once again we have some kind of case study, and we can prove that this expected number of departures in both nodes happen with probability at least 3/4. And so when we sum them, the probability overall is always greater than 3/2. And so when we compute, when we merge all these results together, so the first, yes.
Could you just say out where the assumption of priorities is described? You are the linear slot, you allocate random priorities.
Yes.
Right?
So
where does it show up here?
So here is that so we decide to know whether or not, so the case study happens. The case study happens whether or not node I is actively transmitting during our first time slot. And so we simply enumerate all the cases, all the possible cases that can happen. So this drift it gives us the expected value of what we can get on one jump. So we start from initial condition, we have one jump, and we want to know on average how much each node is transmitting. And so if we focus at node I, so the fact that the allocation priority is uniform happens in computing this this expectation. So on a given priority allocation, the probability that the node I is transmitting is greater than 1/2. So this is what gives us these 3/2 here. And the second way it appears is when you are looking at this term here, we can prove that having node I and I-1 being active and node I+1 being inactive happens only with probability 1/4. And so what we get is the complement of this event. So it happens with the departure in node I-1 and I has a probability, of happening that is higher than 3/4. And so we do the same distinction for the second term, and we sum the two probabilities. And so now when we combine the estimates, so just the drift. So the first term, because the second moment of xi is finite, it is a finite constant that I'm denoting as c. And so we have 8 lambda minus 3, which is quite convenient given the result that we want to prove. And then if we take a good enough constant k, so k is here depending on both epsilon and lambda, we want also this constant to be non-zero and more precisely to be positive. So it gives us naturally the condition lambda that is lesser than 3/8. And so if we use the Stolyar theorem, if lambda is lesser than 3/8, then the drift is always negative outside the segment. And so it gives us the condition that our system is stable for this value. And so for the line topology, we have to be a bit more wary because the n nodes do not have the same number of neighbors as the other one. So we simply make the same case study where they just have to, sorry, there's no lesser than symbol here, it's just a sum. We just have to be wary of the case I is equal to 1, I is equal to n. So for the sum from 1 to n 2 to n-1 for the same as before. But in this case, for the n nodes, there's only one of them that are transmitting. So once again, it gives us the same thing. And because 3/8 is lesser than 1/2, we get the same result that the system is stable if lambda is lesser than 3/8. So this was the first, let's say, mainstream way to prove that a stochastic queuing network is stable. It's rather straightforward, but it relies on first on two main things. The first is being able to find a good enough Lyapunov function. And sometimes it can be proved to be very, very difficult, especially if we do not have such nice temporal evolution for the system. And the second thing is to be able to evaluate this drift, because sometimes the drift calculation can be very hard, especially if you have, on the one hand, the complicated Lyapunov function, and on the other hand, a system with jumps that can be arbitrarily large. So, so these are the two main limiting factors for using this first Lyapunov theorem. Now there is an interesting thing. So if we look at the line, we know that so in the line, actually, this is not the end nodes, but the next to the end node that have the lower probability of transmission. And we can prove, so this is just some computation, but for a line with 4 nodes, the probability of transmission in the node 2 or the node n-1, so here node 2 on the node 3. So this probability is equal to 3/8. And for n is equal to 5, then it decreases a bit, it's 11/30. So we can prove that this probability of transmission actually goes down to 1 minus e to the -1. This is very well known in result, like I said, in Markov-John processes. The system is stable if lambda is lesser than mu. So we can wonder, for example, if in the line topology, the condition lambda lesser than 3/8 is tight, because here we have two different values of 3/8 and 1 minus 1/e. So we can see if we can refine a bit this stability condition. And so now we have to go to another way, because so the first Lyapunov theorem, like we said in the drift, we make some kind of very large upper bounds. So now we're going to be a bit more precise, and we're going to introduce something which is called fluid limits. So fluid limits is something that was introduced by Rybko and Stolyar in '92. And the idea was to study the average of the drift over a large number of jumps in the state space. So instead, on the drift, we're only making the average over one jump. Here, we are making the average of n jumps, and we want to look at what happens when the number of jumps goes to infinity. And so here, so if you take the sequence of processes with an initial condition that goes to infinity, the goal is to study the expected number of R jumps, and we divide the expectation over the number of jumps that we made. And we want to look at what happens when R goes to infinity. So this fluid limit is a very good tool to study the long-term behavior of a Markov process, and it's a very powerful tool because Dye in 1995 proved a very useful theorem. So if a fluid limit is stable, so stability for fluid limit means that there exists a time at which the fluid limit goes to 0 and stays at 0. And so if we have this property, then the Markov chain that we have at the beginning is positive Harris recurrent. And so this is a very, very powerful tool to prove, to easily prove if a system is stable. The problem is that, so the reciprocal is not entirely true. We have to get a weaker condition. So because it was proven that some fluid system can be unstable and the corresponding Markov chain is stable. So we have some kind of reciprocal, but it's not the exact reciprocal for this theorem. But overall, this theorem provides a very powerful tool to prove whether or not a Markov queuing network is stable or not. And so to do so, we have to, fluid limits involve a good representation of the network. And to have a nice representation of the network, you have to be a bit more precise on how you describe it. Previously, we only took into account the queuing length, but now we have to add some definition. So we keep the queue length, and we also have to get the number of arrivals at node I up to time t, and also the total number of departures. So in the same way, we get some kind of queue size at node I at time t. So just the initial condition plus the number of arrival minus the number of departures. So since up until here, it's rather straightforward. And now we have to define a last quantity that is going to be very useful when it comes to evaluating what actually is the number of departures at a given node. So to do so, we are going to take an occupancy state. So the occupancy state is just it's a value, it's a vector. And for node I, it's going to be equal to 1 if the queue length at node I is not empty, and equal to 0 if this queue length is equal to 0. And then we take Q a ranking realization with just the assignation of property. And then we can define something which is called a transmission realization. And it's just going to be a deterministic function on both the occupancy state and the ranking realization. We do not need this function to be explicit, but from the ranking realization and the occupancy state, we can know perfectly which node is transmitting at a given time in the network. And so we have to define two sets, theta and psi, theta being the number of all the possible value for the occupancy state, so which is the set of parts of size n, so with two values 0 and 1. And u is just the set of permutation of n nodes. So theta is the set of all possible values for s and u, and psi is the set of all possible values if we add d to the triplet. And so because this ranking realization and the transmission realization are picked uniformly at random, we can define a probability distribution on theta. And finally, some kind of counting measure on psi. And this counting measure is going to represent the number of time slots during which an event B, transmission realization happened. So for example, such an event can be node 0 is transmitting and node n-1 is inactive, for example. And so this kind of counting measure is going to be very useful because we can see that it can be linked to the number of departures from node I up to time t. If we take the set B is the node I is transmitting or not. And so this last particular counting measure is going to be very useful because it will allow us to bound from above the value of this function and then to give us a condition on lambda for the system to be stable. So now the definition here, we take the Fluid limit. So if we have a subsequence Rn, so it does not necessarily need to be the whole set of integers, but we can take any subsequence. So if each of the component function converges to a fixed limit, to a fixed function qi, fi, hi, and gb, which are the respective limit of the fluid scale process for the Q length, the arrival process, the departure process, and this counting measure that we introduce here. Then we have something which is called a fluid limit for the network. And then we're going to be able to prove the result about stability. So we need this to converge uniformly on compact. And the consequence is that all these functions, all these limit functions, sorry, are going to be Lipschitz continuous and will have all the right properties. We can then have the derivatives and then deduce the result that we want. And using the functional law, the functional strong law of large number, we can get a temporal evolution for the fluid scale system, which is the same as before. If we take the limit, it's just the initial condition fluid scaled plus the arrival process fluid scaled plus the departure process, which is also fluid scaled. And like I said, we have some kind of very nice properties because the fluid scaled arrival process is just the average number of arrivals multiplied by the time. So simply using the strong law of large numbers. And the departure process is just the counting measure of the if node I is transmitting or not. And the last thing that is going to be quite useful is that the derivative of this counting this counting measure G is going to be a probability measure on psi. And because this is a probability measure, we are going to be able to bound everything from above in a very neat fashion. So the last thing, so I'm not going to delve a bit too deep here, but the way to bound from above these probabilities is to defining something which is called friend and foes. And so friends in the network are nodes that are separated from by an even number of nodes, and foes it's nodes that are separated by a odd number of nodes. So here the nodes in red are mutual friends because here this is node 2. The next node is node 4, and 4 minus 2 is even, so they are friends. And on the contrary, here we're node 3 and node 6, they're separated by 3 nodes, and hence they are foes. The nice property about this is that nodes that are mutual friends have a higher probability of transmission because they take the least amount of time, the least amount of space. Sorry, there's the least amount of space between the two transmitting nodes. So overall, the network performance is going to be increased if we add friend nodes to the network. And if you add foe nodes, you are going to decrease the network performance because there is you are maximizing the number of inactive nodes in the network. And then if you take occupied segments, so segments of contiguous nodes that have non-empty queues, you can prove that, for example, in this case, the edge nodes of an occupied segment have a higher probability of transmission if you add friend nodes to this occupied segment. So I'm not going to, so I won't have time to make the computations to show you the computations for this. But as an outline for the proof in this, the goal is going then to find a constant epsilon that is strictly positive, such that if we take a regular point at which the norm of the queuing, the queue length at a given time is strictly positive, we want the derivative to be strictly negative. And so this way, whenever there is one queue that is positive, we are going to be drawn back to 0. And so this is going to prove that if the free limit is reaching 0 at some point, then it's going to stay at 0, because if at a given small interval of time, it's bouncing back from 0, then it's going to be drawn back using this this condition. So if all the nodes are active, it's quite easy to prove using this this equation here. If we take the derivative, then it's just lambda minus the probability that node I is transmitting. And we can prove that this probability actually is equal to the jamming density in a circle for each node I. And so if we make the sum over n, we have a very simple condition that lambda has to be lesser than Cn over n. So another result that is from the parking problem, you can prove that Cn over n, it's a non-increasing sequence for even values and a non-decreasing sequence for odd values. So if you take the subsequences along the odd and even indices, you do not have the same behavior. But what's true is that these two values are always higher than 2/5, sorry. Here, because so for even values, it's higher than the limit because it's a non-increasing sequence. And for the odd values, it's higher than the first term. So here n is equal to 5. And you can compute that n is equal to 5 is achieved when n is equal to 5. Sorry, 2/5 is achieved when n is equal to 5. So here it gives us a nice condition. If all the nodes are active, then lambda has to be lesser than 2/5 for the system to be stable. And actually, it also works if you have some nodes that are inactive. And so the outline of the proof is to reduce the analysis to something which is called positive groups of size L. There are groups of nodes that are all that have all a non-empty Q length, with the nodes outside that are bordered by 2 empty Qs. And so we can reduce the analysis to these positive groups, and we have to make a case study about the length of these groups. So with L is equal to 1, it's rather easy to get some kind of upper bound for the drift here. We can easily solve it for lambda. So 5 lambda has to be lesser than 2, then lambda has to be lesser than 2/5. For L is equal to 2, L is equal to 3, we have some kind of the computations are quite tedious here. But we have this condition that 5 lambda over 2 minus 1 has to be positive, has to be negative, sorry. And if L is equal to 4, actually we are just grouping all these cases by saying that one of the worst occupancy states, it occurs when we have a segment of line 7 with the middle node transmitting. And so this happens with probability, so 179 divided by 420, which is greater than 2/5. And so just by making, so I voluntarily did not show any of this computation because it takes pages and pages, but it's very dependent on the probability phi that we defined here. By making the right conditioning using this probability distribution and the concept of friend and foes, it's easy to bound the events from above, and then to get these bounds for the drift of the Q, the fluid scale process. And then in this case, using this theorem from Dye, we have proven that if lambda is lesser than 2/5, then the system is always stable for the circle topology. But this thing actually is not very surprising because we've seen that Cn over n is always greater than 2/5, and by using the same very classical result in queuing theory, if the average number of departures is higher than the number of arrivals, then the system is always stable. And because the average number of departures is always lesser than 2/5, then this condition actually is not very surprising. But what is a bit more surprising is that we have the same stability condition. Sorry, I messed the title of the slide is the stability condition for a line. So like I said, here we have this link between the two jamming constants. And it gives us that ln over n is also greater than 2/5 using the same kind of arguments. And now for the line, so we are using this same argument. So if all the scaled Q length are positive, then we want the drift to be always negative. And so we have the same equation. So here, instead of having the jamming constant on the circle, we have the jamming constant on the line. And this is negative if lambda is less than 2/5. And for the rest, we have the same case study as before. We just have to take into account the border nodes and the next two border nodes, which have a lower probability transmission. But in the end, everything is still bounded in a similar fashion. And the same result is holding, is that lambda is lower than 2/5, means that the system is stable. But here, we saw that for the line, actually, you have some nodes, so the next to the edge nodes that receive a throughput that is lesser than 2/5. And so this shows that the result is very not intuitive, because even though some nodes have a throughput that is lower, the overall topology kind of averages out this side effect from the next two border nodes, and it still gives us a stable system, even though locally the arrival process is higher than the departure process. And so for the circle topology, so just some summary of the conclusion that we have here. So here the stability, so we increased it. So at first we saw that it was the stability bound was lambda less than 3/8. It was increased to 2/5, so 4/8. Sorry, no, so from 3/8 to 2/4, sorry. Now the question is, so we know that we can compute the limit. For example, here the limit for Cn over n is a half of 1 minus e to the -2, and it's approximately equal to 0.43. So we went from 0.375 to 0.4. Now the question is, can we go all the way up to this limit? So it's still an open question. So if anyone has ideas on how to prove it, there's some work to be done here. But the stability condition, if lambda is lower than this, is still an open question. The same goes for the line topology. Can we go higher than 2/5, or is it a bound that starts to be too high because of this node that received a lower throughput? So this is the end of this paper. So the reason I picked it is because it shows two very interesting ways to prove the stability for a queuing network. So we have the classical mainstream way of using the Foster technique that still requires some kind of mastery when it comes to finding the good Lyapunov function that will give us the right stability condition. And now we found a more refined version using fluid limits. And the fluid limit actually was quite ingenious in the way that they define this this probability distribution, because once this quantity is defined, actually it's linked to the derivative of the fluid scale process, and all the calculations actually are done. So it's a bit tedious, but it's quite easy to bind everything from above when once you take the right conditioning on the events. So this was the thing that was quite ingenious in this paper. So because the references did not pass, so there's this article from Dye that proves this this thing between positive Harris recurrence and fluid limits. The original article from Rico Stolyar, so it was written in Russian, but it has since been translated in English. So where the discrete scaling is introduced. And the last thing is another article from Shneer and Peter van Deven, where they compute everything linked to this discrete parking problem, that all these probabilities that are used here. So if you want to take a closer look to the computation that were made, the article is quite short. It's only 6 pages long, but quite interesting in terms of combinatorics. So this is the end of the presentation. So thanks for attending, and if you have any questions, you can ask.
Okay.
Right.
So the fluid limit is used to give the right stability condition. But if I get it correctly, because they use bound to estimate. They only use certain condition for the fluid to be zero, right?
Yes.
Using some bounding.
Yeah.
So it's like, well, it's likely that in this case, there will not be bound to look at the certain conditions for the fluid to zero. It would be the right condition.
So actually, so it can be a way to do it. So try to use as few bounds as possible in the computation. Another way is that I said for this Dye theorem here, sorry, we don't have a direct reciprocal, but there is still some kind of reciprocal that was also proved by Dye. So he wrote a lot of stuff about fluid limits. But there is a definition for something which is called weak instability for the fluid system. And weak instability, so it's a definition that is similar for weak stability in Markov processes. Weak instability states that if at some point for any given fluid limits Q then Q and a given time delta, if Q delta is strictly positive, then we are ensured that the fluid limit is never going back to zero past this point. And so we can prove that it implies that the population of the Markov chain is growing to infinity. So one way is to not use any kind of bounds to prove the stability, and then to get an exact an exact stability condition. The other way is to use this definition of weak instability to actually try and see if the system is unstable if lambda is greater than 2/5. And so this would be a way to get the equivalence. So yeah, so this is the two competing ways. So either not to use any bounds and to try and compute the exact value of lambda for which this drift is going to 0, or just to try and prove the reciprocal using another definition for instability.
Are there any questions on the bridge? François, go ahead.
So, it looks like so if you could think of the grid or the storage into your higher dimension,
yeah,
there will be similar questions. So can the technique or where the technique used to assess what happens in higher dimension?
So to know if instead of having, so here we have only here we have a graph where each node only has 2 degrees. So the question is if we, for example, take 3, 4, 5, or n the degree n that is the same for all nodes, does this technique still work? So not that I know of, and this is one of the open questions that is asked by the authors at the end of the paper. My intuition is that it's definitely doable using the same kind of tools, because here, so it mostly appears in the departing process. So my guess is that it's possible to adapt some of these definitions to the case where we have a given number of so larger n larger than 2 neighbors for each node in the network. It's going to change the way this occupancy state, the ranking realization are made, but eventually I think it's totally doable to adapt this to a higher dimension. Among the open questions at the end of the paper, there's also the question of multi-hops network. So here it was only a single hop. So we only deactivate the neighboring node. So what happens if we have a m-hop network where you decide to deactivate the m neighboring nodes in the network when you are transmitting? So it seems that they were playing around with a model with the m is equal to 2 and with 4 nodes that they managed to adapt this tool. So my guess once again is that it's also doable by trying to adapt some of these techniques. One of the limiting factors is to find right ways to bound everything so that we have a meaningful bound. So not that the bound is lambda is equal to 0 because it's trivially stable, but my guess is that it's also doable using the right definition.